Assalamualaikum and salam sejahtera to all students. Today our lecture is about bipolar junction transistor BJT for AC analysis of BJT. Okay, this is the learning outcome. At the end of this chapter, students able to analyze the small signal of single-stage BJT amplifier circuits, calculates the transistor parameters such as voltage gain, current gain, input impedance, and output impedance Zout. Alright, now we go on to the next slide, which is the introduction. Increasing the power of an AC signal is called amplification. Increase the power level, make it a weak signal become more stronger. Amplification circuit called amplifier, example BJT, bipolar junction transistor. The amplifier properties is that it can be categorized into four. Number one is voltage gain AV, current gain AI, input impedance Zi, and output impedance Zout. For a good amplifier, it must have a high voltage gain, high input impedance, low output impedance, and also high bandwidth. Okay, before we proceed to the next slide, we now begin to examine the AC response of the BJT amplifier by reviewing the models most frequently used to present the transistor in the sinusoidal AC domain. One of our first concern in the sinusoidal AC analysis of transistor network is the magnitude of the input signal. It will determine whether small signal or large signal technique should be applied. Okay, there is no set dividing line between the two, but the application and the magnitude of the variables of interest relative to the scales of the device characteristic will usually make it quite clear which method is appropriate. So we have to look at each of the method, and we have to make sure that we choose the best method for certain configuration circuit. Okay, circuit configuration. Alright. So there are three models commonly used in the small signal AC analysis of transistor network: the RE models, the hybrid pi model, and the hybrid equivalent model. This chapter introduces all three but emphasizes the RE model. So we touch on the hybrid, but our emphasis is on the RE model. Alright, so we go on to the next slide. In this chapter, we learn how to analyze and work with a single stage amplifier, to examine AC response of BJT amplifier by reviewing models frequently used to represent the transistor in AC domain. Amplitude of the input signal will determine whether to use small signal or large signal analysis technique. Okay, we go on to the next slide. Okay, this is the transistor equivalent model. A model is an equivalent circuit that represents the AC characteristic of the transistor. A model uses circuit elements that approximate the behavior of the transistor. There are two models commonly used in small signal AC analysis of a transistor. As I mentioned before, this is the hybrid model, and the other one is RE model. But we are going to use the RE model in our exercises. So let's go on to the next slide. Okay, this is the hybrid model, pi. The hybrid model is most useful for analysis of high frequency transistor application. At lower frequency, the hybrid model closely approximates the RE parameters and can be replaced by them. So as you can see here, and this is the small signal AC equivalent circuit of a BJT. This is the uh, electrical symbol for BJT. This is P and P. Uh, Sorry, this is NPN transistor, where the current move from base to the emitter. So here is the AC equivalent circuit. Okay. Uh, okay, so you need to understand that if you want to change the uh, circuit from this AC equivalent to this AC equivalent small signal AC equivalent circuit, you need to remember all this notation here: RBB prime, R pi, GM, V pi, and also RC. Okay, in RE model, there will be beta RE over here, since we say that RBB is approximately, or we can neglect RBB if it is very small, so we can say that there will be only one resistor here. But if the question give you the value of RBB, so you need to include RBB in your network. So if not, RBB will be neglected and this will be short, and there will be beta RE over here, that is for RE model. Okay, now I'm referring to RE model. This will be beta RE, and this will be beta IB. Okay, and this will be RO. So as you can see here in the equation given here, GM V pi is equal to beta IB. So beta IB is the current that flow from the C, or collector point, to the emitter. IC we can say approximately to IE. So in this case, the emitter terminal is connected to ground. So RE is equal to VT over IE, and it is equal to 26 millivolt over IE. This is actually a formula if you want to find the value of RE. Okay, but if it is not but if it is given in the question the value of RE, so you just simply put the value in the equation. So R pi is equal to beta plus 1 RE, and it is equal to beta plus 1 VT over IE, since RE is equal to VT over IE. So it is also approximately to beta VT over IE. Alright, so now we go on to the next slide. This is for RE model. BJTs are basically current control devices. Therefore, the RE model uses a diode and a current source to duplicate the behavior of the transistor. One disadvantage of this model is that its sensitivity to the DC level. This model is designed for specific circuit condition. The use of RE model then becomes more desirable because an important parameter of the equivalent circuit is determined by the actual operating condition, but one must still turn to the data sheets for some of the other parameters of the equivalent circuit. The RE model also failed to include the feedback term, which in some cases can be important. So the RE model is really a reduced version of hybrid model, and it is used extensively for high frequency analysis. Okay, So this is the RE transistor model, as you can see here, compared to the hybrid. So hybrid model, you have RBB prime, RPi, GMVPi, and also RCE. For RE transistor model here, as you can see, let me increase the size of the page. Okay, so for RE transistor model, as you can see here, this is beta RE, this is beta IP, and this is RC. RC is actually equals to R naught. Okay, alright, so this is transistor AC equivalent circuit for common emitter, and this is transistor AC equivalent circuit for common base. The difference here is that the current that flow for a common emitter, the current will flow from collector to emitter. For the common base, the current will flow from collector to the base. Okay, this is the emitter point over here. Alright, now we go on to the next slide. Okay, small signal AC equivalent circuit procedure. Okay, first we need to replace all capacitor with short circuit and set DC source to 0. So remember, if you want to analyze for AC equivalent circuit, the first step is to replace all capacitor with short circuit. Remember, capacitor must be in short circuit and set DC source to 0. If you set DC source to 0, what will happen to your DC terminal? It will be grounded. And number 2 is substitute BJT with hybrid model. Okay, it depends on your question. So if it doesn't say anything about hybrid model, you can just use RE model. Okay, so these are all examples of the circuit starting from figure 1, 2, 3, and 4. Okay, you need to try to draw the small signal AC equivalent circuit based on the configuration. Okay, these are the exercise. Okay, let us look for the first one. Okay, the first one is the common emitter bypass RE. The meaning of bypass RE means that the current does not flow through RE. And if it is bypass RE, means there should be a capacitor connected in parallel with your resistor RE, so that the current will not flow through RE during AC analysis. It will flow through capacitor CE over here. Okay, that is what we call as bypass RE. Okay, the first step, replace all capacitor with short circuit and set DC source to 0. Okay, so if you set DC source to 0, what will happen to VCC? Will be grounded. Okay, so here, as you can see here, R1 will connected to the ground here. RC will connected to the ground here. So you can put your R1 over here. You just change from this terminal, ground terminal, to this ground terminal over here. So you can see here, right? These are all grounded. Okay, so you just can put this terminal over here, change it to here. So R1 will become here. Okay, alright. So you can see this in this simplified AC equivalent circuit, where you have changed your R1. So R1 will be down over here, and then it is parallel with R2 and connected with your BJT over here. So this is an NPN BJT. Alright, so it will be connected from here at this point, at the collector point over here. It will connect to RC and connect to ground. So it will connect to RC and ground. Alright, okay, so this is the simplified AC equivalent circuit. This is not the small signal AC equivalent circuit. If you want to change this circuit to uh, what we call as a small signal AC equivalent circuit, we need to consider this circuit, okay, this model. So substitute BJT with hybrid model, or you can use the RE model. So if you use RE model, this will be beta RE, this will be beta IB, and this will be RO. Okay, all right. So after you have substitute this uh, model to the simplified AC equivalent circuit, you will get this kind of circuit over here. Okay, so this transistor, you change it into this circuit and you will get this circuit. So this is to determine the BJT model parameter. For example, you want to find input impedance ZI, output impedance ZOut, voltage gain AV, and also current gain AI. Alright, so this is the amplifier with the hybrid equivalent circuit. After you have simplified the circuit, okay, you can get like uh, this, okay. So you have simplified it. So simplified hybrid equivalent circuit for of a CE common emitter amplifier, CE amplifier. So this is the simplified circuit of the small signal. Okay. Okay. So for RE model, this will, you can ignore RBB if it is too small, but you need to remember this will change to beta RE, and this will be beta IB. The current here will be beta IB, and this will be RO. Okay, for RE model. Okay, alright. So the analysis start from the input impedance. So first you need to find what is the input impedance. Okay, input impedance you have to look from the input side. So this is the input side. Okay, like this. ZI over here, as you can see here. Alright, we look by from the input side. So you can see that from here R1 and R2 is parallel. Okay, you can see here this is R1 and R2 and connected to your BJT. BJT you will change to AC small signal equivalent circuit, so it will be connected to beta RE, or for for hybrid parameter it will connect it to RBB prime and R pi. Alright, so here you can see here Zin is equal to R1 parallel with R2 parallel with ZB. ZB is actually the base impedance. So this is your base terminal. So anything here is actually referring to your base. So the voltage here is actually your VB, or base voltage. So if you want to find the impedance here, you should get VB over this current. Eh? That is Ohm's law. So impedance is equal to the voltage divided by the current. Alright, so if you want to do the what we call as uh, equation, okay, you can find that VB equal to IB times RBB prime times R pi. So IB in bracket RBB prime plus R pi. Alright, so here you can get the ZB, that is IB multiplied by RBB prime plus R pi divided by IB. That is your ZB. Okay, so if you simplify this equation, you will get RBB prime plus beta plus 1 RE. Okay, that is if you simplify this equation. Alright, so that is for the input impedance. Now we look at the voltage gain. Alright, so this is the voltage gain. AV equals to V out per V in equals to V out per. This is actually VB. This is not VE. Please correct this error. This is actually VB, base voltage. So because base voltage is the input voltage over here. Okay. This is V in. This is VB. VB is at this point over here, at this terminal over here. So V out over VB equals to minus GM V pi multiplied by RC parallel with RCE over IB multiplied by RBB prime plus R pi. You can use this equation if you are using a hybrid model. But if you are using RE model, so you can change this GMV pi to V beta IB, and you can change RBB prime plus R pi to this. Okay, R pi equals to beta plus 1 RE. Alright, so by substituting all this equation into the what we call as RE model, you can get AV equals to minus beta IB multiplied by RC parallel with RCE over IB multiplied by RBB prime plus beta plus 1 RE. Okay, why there is a negative sign over here? It shows that the current is flowing in different direction, or maybe you can say opposite direction. Just now you see that this current is flowing from collector to emitter. So if you want to find the output, you need to change the direction of this current and flow to this direction. So this will be minus, okay, or you can say minus beta IB. Alright, so that is why we have this negative sign over here. So you simplify this equation, then you can get this equation over here. Alright, so now we go on to the current gain. But before that, we have to look at the output impedance. So the first thing you need to do is to set V in to 0. So if you want to look at the output impedance, set input voltage to 0. Therefore, V pi equals to 0, GM V pi equals to 0. As open circuit. Okay. Alright, so from here you can see that RC is parallel with RCE. That is your V out. Sorry, Z out. Okay. Alright. So that is your Z out. Okay. Now we go on to the current gain without RL. RL is your load resistance. So to find current gain, AI is equals to AV multiplied by Z in over Z out. Okay, so from here you can get your AI. Okay, let me show you. If you can see, AI is equal to AV ZI over Z out. So, oh, sorry. AI equals to AV multiplied by Z out over Z in. Alright, AV equal to, so you look at the equation that you have, equals to minus beta, minus beta RC parallel with RCE over RBB prime plus beta plus 1 RE. Or you can just say that, oh, never mind. Let me show you first. So look at Z in equals to R1 here AI equals to AV. ZI is R1 paired with R2 paired with ZB. Okay, and Z out is RCE paired with RC. Okay, this is when RL when there is no RL. Okay, load resistance. This is your load resistance. Okay, so just substitute AV into the equation. So just substitute AV into this equation over here, and from there you can find AI. Okay, alright, so that is all for today's lecture. I will continue the next lecture in the next slide. Okay, so I think that is all for today. I will continue this lecture for common emitter unbypass for the next lecture. So here is the exercise. So you guys can try this exercise 1 over here. So if you have any question, just give me a message in our Google Classroom. So thank you very much. Assalamualaikum and salam sejahtera. Bye.